The title of this session is Upgrading Food Delivery Services by Machine Learning at Demaecan. Hi, I'm Hongbo Zeng from Data Science Center. Today, I will cover these topics. Starting from the background of services offered by Demaecan, followed by the outline of 5 machine learning components to be implemented, and a deep dive into 2 of those components. Let's begin with the first topic, Demaecan's services as a background of this talk. I'm sure you have either used or heard of Demaecan's food delivery services. They are already 20 years old, having launched in the year 2000, and still growing and expanding, with more than 80,000 merchants and over 7 million active users as of August this year. To cope with such growth, they are currently undergoing major system updates and implementing machine learning to improve experience of all those who use their services. I'm going to share with you today some of such initiatives. Now, machine learning can be applied to multiple areas of Demaecan's services. Let me start with how their services work. Out of multiple service modes they have, I'll focus now on sharing delivery, where most of the machine learning implementations concentrated. In the sharing delivery service session, there are 3 actors other than Demaecan, namely the user, the merchant, and the driver. First, the user places an order from the app or website, and the merchant and the driver are notified. The merchant starts cooking. The driver has a choice of either accepting or rejecting the offer. Upon acceptance, the driver goes to the merchant, picks up the dishes, and delivers them to the user. We looked through this process to see where we have machine learning opportunities, and eventually identified 5 areas to offer machine learning components. I will now go over the outline of those components and later pick up 2 of them to further describe the details. Now, in this segment, I'll give you an overview of 5 machine learning components. Each of them will be explained starting from the tasks defined, challenges of the tasks, and our approaches in accomplishing those tasks. The first component is where the user places an order. There are so many merchants to choose from, and it's simply impossible to go over all of them. When I tried, I found hundreds of merchants available in my neighborhood. If you want to find an interesting merchant you've never tried before, you may want to consult with the popularity ranking, which, however, by definition, represents popularity within the entire area of your greater neighborhood and therefore may not represent your own preference. So, we came up with the first machine learning task to offer users with personalized recommendation of merchants. In this recommendation problem, for this type of services, you have to realize users can place orders with the same merchants repeatedly, different from other line services like manga and stickers. If you tune and select your model for accuracy alone, you tend to recommend those merchants the user has used in the past, not a very valuable recommendation, as the information is available in the older history. In general, your recommendation looks similar to the ranking and again not valuable information as the user can always turn to some ranking website to find those merchants. Therefore, recommendations accuracy must be balanced well with components of discovery and discovery diversity for the user. So we decided to use multiple metrics to tune the model, such as entropy for diversity, in addition to NDCG for accuracy. Another similar yet different challenge is the bias of food categories in the recommendation, like curry places only or sushi bars dominant list, which is not desirable to suit the user's preference at that particular moment. We therefore implemented a two-stage model where we combined multiple models to reduce such biases. I will come back and talk more about this later. Next, I want to go over two machine learning components associated with the delivery lead time, once again related to the user's decision. The recommendation helps the user to decide what to order with which merchant, but the user would also want to know how long it'll take for the order to be delivered. You don't want to wait for 2 hours with an empty stomach. After you decide, it'll be also nice to know a driver has been assigned or where your orders are right now, together with estimated arrival time updated over time. Such delivery time prediction requires multiple assumptions and conditions. Does the user know what to order before connecting? Has the driver been assigned, etc.? Too much for a single machine learning model to handle. We decided to divide the process in multiple tasks. How can we divide the delivery lead time, indicated in this chart as a white arrow? First, there is food preparation time, and then the time that takes for the driver to travel to the merchant. It's called shop arrival time. On the chart, driver's arrival time is shown as being after the food is ready, but of course that can be before. And in that case, the driver has to wait for the chef to finish cooking. Then the final component is for the driver to travel from the merchant to the destination. So the delivery lead time equals the larger of the food preparation time or the driver's travel time to the merchant plus the final leg of the trip to travel to the destination. Out of these three components, we decided to apply machine learning to predict the first two components, the driver's arrival to the shop and the food preparation. Why not the final components? Because we know the starting point, the merchant, and the destination. Map and navigation route information can give you a pretty accurate estimate of time it takes without the help of machine learning. In that case, why the first component? We know the location of the merchant. Well, the prediction must be made before who the assigned driver is and where he or she is, and we don't know how long it may take to find the driver who accepts the offer. The simple map and route information will not be sufficient. These tasks have a common challenge. Prediction depends largely on the situation at the time. If the merchant is busy, it'll take longer to cook the food. If there aren't too many available drivers around, it may take a while to find one who accepts the offer. This challenge is resolved by giving the model the real-time feature collected by streaming processes. The food preparation time has its unique challenge. That is, we cannot log the exact time the food is cooked and ready to go. How to address this challenge is a topic for a subsequent section, to which I will come back later. Now I've covered two machine learning components for predicting the delivery time. Let me now switch gears and talk about machine learning components from the driver's perspective instead of the user's. The driver has to be waiting somewhere to receive offers for pickup and delivery. And of course, she would want to be waiting in an area with many popular eateries likely to receive orders so that she can minimize the time to get to the merchant and the entire delivery lead time as well. Certainly, there'll be less hustle for the driver when that's possible. So the next task to consider, therefore, was to predict the number of orders for different areas and different times of the day. When we define a relatively large area to make predictions, we end up with less accurate predictions, but with a larger amount of data. But what is needed in this case is a more granular predictions for smaller areas with less data to train the model. So we decided to train a single model with data from all the areas. We also fed the model with historical data of orders and other features to represent differences among different areas. Just like in the previous delivery time prediction, situations at the time can make a lot of difference in the number of orders. For example, it starts to rain shortly before dinner time. Rather than going out in the rain for grocery shopping, you may decide to use Demaecan services to get your dinner delivered. When there are many others like you, the number of orders can spike. So that's been about order forecast task. Lastly, let's think about order-driver matching. By matching orders with drivers, you want to achieve the most globally efficient delivery operation. I know it sounds easy, but it's easier said than done. Multiple orders to be allocated to multiple drivers sounds like a classic optimal assignment problem, but not quite. An offer to deliver an order is not forced onto any driver. The drivers may either accept or decline the offer. If you sequentially repeat the offering process every time a driver declines, it'll take too long to find one, so you also want to be able to send the same offer to multiple drivers. Also, the order-driver matching is not the only factor behind the overall dispatch efficiency. The food preparation time at the merchant, for example, is an important variable in this food delivery industry that has to be predicted well. Let me explain by using this diagram. Users A, B, and C placed their orders to merchants A, B, C, respectively. There are available drivers 1 and 2. Driver 2 is closer to merchant A, but if the food is not ready when the driver arrives, she will have to wait there idle. That'll be a waste of time. In this case, it may be more efficient to send the driver 2 to merchant C a little farther away and assign driver 1 a little farther away to merchant A. Needless to say, to achieve the maximum efficiency, such dispatch decisions have to be made near real time. You don't want your users to wait for 5-10 minutes before that decision is made. For this particular task, we built a simulator to simulate daily orders and dispatches using actual data from merchants, users, and drivers. We are evaluating the efficiency of dispatches using this simulator. In these diagrams, order-driver matching looks like a one-off event, but in reality, matchings and dispatches are done repeatedly. Order dispatch efficiency should be looked at from a longer perspective, therefore. For that purpose, we are considering the use of reinforcement learning. Let me summarize this segment in which I've given you the overview of 5 machine learning components. For the user, we have recommendation system to help choose a merchant, and preparation time, and the driver's shop arrival time predictions to estimate the delivery time. We also have order forecast for the driver and the order-driver matching. In the next 2 sections, I'll do a deep dive in recommendation and food preparation time prediction. Case Study 1. Recommendation for the users to decide on her order. The task was to present a personalized list of recommended merchants reflecting her preferences. This task entails a challenge of 2 types of diversity. First is overall diversity of merchants to be recommended. Multiple users are presented with different recommendations. When looking at the collective pool of recommended merchants, do we have sufficient diversity? In other words, are we sure we are not presenting similar recommendations to everybody? Recommending same or similar merchants to any user is never desirable from the fairness to merchants perspective and result in bias towards highly popular merchants. Popular merchants information is available from any ranking websites and does not give you differentiation. The other type of diversity is for genres or categories within a single list of recommendation. Curry only or sushi only list is boring and does not respond to the user's preference at the time. And eating the same thing every day is not healthy. One thing you have to be careful about diversity is that there is a trade-off. The trade-off between diversity and accuracy of predicting what the user actually orders. I will come back to this dilemma, but now let me discuss how we addressed these diversity challenges. First, overall diversity of merchants. The problem here is that there is a large amount of information about popular merchants, and learning with such data can result in popularity bias. So we tweak sampling for training and evaluation to reduce the bias. More specifically, for evaluation, we apply sampling weight, inversely proportional to popularity. For training, similar weighted sampling can be done. How much trade-off to be reduced can be tuned using hyperparameters. For exploration and selection of hyperparameters, we used tools like Optuna. This weighted sampling method for reducing biases was not developed for this project from scratch. Instead, it's offered in Masala framework that we've developed. If you're interested, I talked about the framework at last year's Line Developers Day, which can be found here.
Here are the results of evaluation using the actual sample data. Here's a graph. Each point corresponds to a model, which can be called a combination of hypervisor. The horizontal axis is an NDCG, index for accuracy. The vertical axis is the entropy index for overall store diversity. And each point represents a model for both indices. The higher the value, the happier the model. A blue model means that there is a model that is further to the right than each of these blue points. So the model has a good trade-off between accuracy and diversity. It is difficult to evaluate which of these blue models to use offline, so it is better to select some of them and run them through online tests and evaluate them by looking at the conversion rate index, for instance. The above is an evaluation of overall diversity of restaurants. Let's think about the diversity of genres here. The embedding model often used in recommend, such as graph neural network, is known to be highly accurate but tends to reduce the diversity of genres. On the other hand, co-occurrence recommendation models and point mutual information PMI models, which use co-occurrence information for predictions, are known to have higher genre diversity but lower accuracy than embedding models. Therefore, we are trying to secure both accuracy and genre diversity by combining the two models. Specifically, we use a model using co-occurrence information to roughly select candidates' restaurants, and in the second stage, we use an embedding model to rank them in more detail while taking into account the stores or restaurants from the first stage. Now, let me show you the result of the experiment with this model. In addition to NDCG and entropy metrics that I mentioned earlier, I added a new metric called intra-list similarity. This is an indicator that shows how similar the indicators in the recommend lists are. For now, it is better if they are not similar, so the smaller the value of this indicator, the better. The first line, GNN, is an embedding model, and the second line, two-stage model, which combines a PMI model, is the third line. Comparing the first line with the third line, similarity is decreasing and genre diversity is increasing. So we can see that this approach is correct. Also, NDCG and entropy have increased, which may be due to the ensemble effect of combining models with different ways of thinking to increase the overall accuracy. This is a summary of the efforts to develop a recommendation system at Demaecan. In the development of this project, we had to deal with the issue of two types of diversity, and for the overall diversity of restaurants and stores, we tried to use a stage model, two-stage model with sampling based on the popularity of restaurants. For the diversity of genres, we used a two-stage model. Now let's move on to the next section. In this section, we will consider the preparation time of food. First, let's review what we wanted to do. In the end, what we wanted to do was to predict the delivery time of the food, this part of it, predicting the time from when you order the food to when the food is ready, is what we wanted to do in this section called cooking time prediction. It is important to note that food preparation time is not only the time it takes to cook the food, but also the time it takes to pack the food. Now, I faced several challenges in tackling this task, and I'd like to talk about three of them. The first is the problem of not being able to accurately capture the time at which the food was prepared. The second problem is that there is not enough data in some areas of restaurants. The second is that there is not enough data, and therefore the third problem is that the idea is subject to be predicted will vary according to the latest situation. In the following, I will discuss the details of each of these three issues and how we are addressing this. Let's start with the first challenge, the lack of accurate logs. And you might wonder why there is no accurate logs. In the Demaecan, the driver's app and the merchant's app are used. For instance, the delivery of food order, the app is operated by the driver or merchant staff when the food order is accepted, and the timing of the operation is logged. However, the merchant app does not have a button to indicate when the food is ready. While it is possible to add such a button, it will be undesirable due to the operational burden on the restaurants. Therefore, we decided to approximate the food preparation time by using two timestamps that we currently have. One is the order time when the user orders the food, and the other is the pickup time when the driver says he has picked up the food at the restaurant. The difference between these two timestamps is used to approximate the food preparation time. However, There are two major problems with using this method as is. Let's look at them in order. The first one is that the time when the food is picked up is not always the time when the food is received in the log. Let's look at this in detail. Tap, the driver is responsible for order delivery button. Tap the receive button when the driver receives the food from the restaurant, and tap the delivered button when the order is actually delivered. This is a correct specification as it is supposed to be. It's the right tap at the time. However, this is not the case for all the data. In some cases, for instance, the user taps the food delivery was delayed button, but for some reason, the store receiver does not tap the button but taps two buttons together at the end. For this kind of data, we use GPS logs to cleanse the data. Specifically, we looked at the GPS data of the driver, the timing of the tap, and at the timing of the tap to pick up the food. The GPS location was far away from the store, and we excluded this data from training data evaluation data. We can't treat this data as easy yet, although we cleanse the data, because there is a time lag between when the food is ready and when the driver comes to pick up. For instance, if the food was ready and the driver took 10 minutes to drive, then the pickup time of the driver is 10 minutes later than the time of the food preparation. Then the timestamp of the driver's pickup time is not credible as timestamp of the completion of the food preparation. This issue was also addressed by using a driver's GPS log. Specifically, we divided the data into two cases. Case 1. This is a case where the driver waits for a certain amount of time to get to the restaurant and pick up the food. When the driver arrives at the restaurant, the food is not ready yet, and the driver picks up the food after it is ready, so the driver's pickup time can be trusted at the time when the food is ready. On the other hand, case 2, if the driver picks up the food immediately after arriving at the restaurant, the food is ready before the driver arrives at the store, so the driver didn't have to wait to pick up. Therefore, the driver's pickup time is not reliable as time of the food is ready. It is possible to train and evaluate using only the data on the left-hand side, which is creditworthy, but we had a lot of data on the right-hand side as well, so we decided to use both. Of course, this does not mean that we use the data as is. In this case, we devise a loss function. Let's look at the next slide. If you look at the graph on the left, the horizontal axis is the predicted value, and the vertical axis is a penalty against the predicted value. Let's say that the time the user places an order to the time the driver completes the pickup is 5 minutes. 5 minutes correspond to this vertical dotted line. In machine learning, the prediction will be made at the point where the loss function, penalty, and loss values are the smallest. Let's assume that the data is from a reliable one. If the driver waited at the restaurant, since the completion time of the food is 5 minutes, we use the orange L2 loss function, the abnormal error function. In this case, the minimum point of this function is 5 minutes. As I mentioned earlier, the 5 minutes when the driver completes the pickup is almost equal to the 5 minutes when the food is completed. So we want the prediction to come here. On the other hand, let's assume that the data is unreliable and the driver did not wait at the restaurant. In this case, the driver completed the pickup in 5 minutes, but the food is not actually ready until before 5 minutes. We will use the custom loss function that we use for the green unreliable data. We note here that the minimum point is smaller than 5 minutes. This reflects our intention that the completion time of dish should be faster than the actual pickup time we just did. And see the equation on the right to see how much to shift to the left or to the smaller side. It is determined by using value L prime. Alpha is a value that determines the date of the endpoint, but it is a hyperparameter. In addition, the minimum point is shifted to the left, but please pay attention to the left right asymmetry as well. This reflects the intention to give a larger penalty if the time is greater than 5 minutes, since we are sure to be wrong, and a smaller penalty if the time is less than 5 minutes, since we don't know the exact time the food was cooked, so we should be generous. This was our approach to the task of not knowing the exact time the food was ready. Next, let's consider the second task. This is a problem of biased data where there is a little data by region or area. First, let's look at the map of the region of bias. This is dummy data. I use this to give an idea. Each hexagon represents a region, the darker areas represent areas with more odors, and the lighter areas represent areas with fewer odors. You can see that the areas with high odors are limited, and most of the areas have very low odors. The same is true for restaurants. Histogram, the horizontal axis is the number of orders received by a store over a certain period of time, and the vertical axis is the number of stores with numbers of orders. We can see that while some restaurants have certain amount of orders, for many restaurants, the number of orders is low. If we simply create a model in this state, we may end up with data that only accounts for a large number of orders, and the aggregated value may become unstable when aggregated to create features. So we need to be creative. Now let's look at the model first. One by one. First of all, in this task, we decided to use LightGBM as a model. The reason for using LightGBM is that gradient boosting decision tree uses multiple decision trees to make predictions. The reason for using LightGBM is when creating a new decision tree, it focuses on learning points that are not well predicted by the decision trees created so far. Therefore, it is expected that the prediction will be reasonably stable even for stores with certain amount of small data. Also, from a viewpoint of prediction accuracy, deep learning models can be compared, but LightGBM is more lightweight and is known to work well when the number of data is not so large. In this case, we decided to use LightGBM. Next, let's look at features. First, let's talk about smoothing the target encoding. To begin with, target encoding. What is target encoding? In a nutshell, it's the average target value by category. Specifically, category refers to restaurant and regions, and target refers to the preparation time. So the category, the average of preparation time for each restaurant and region, which is the target encoding. By adding such feature, the model is able to focus on the difference between the average value of each category and the individual instances, which is known to facilitate successful learning. On the other hand, the drawback is that the aggregation becomes unstable when the number of data is small. So this time we decided to smooth the target encoding. Specifically, I took the weighting average of the two averages, the average value for each category and average value for the entire category, regardless of the category, and use this as a smooth target encoding. And for the overall average, W is a hyperparameter, and with this smoothing, even for fewer data, we can have the stable target encoding. The second feature is image feature. The idea behind this is that even if the restaurants and regions are different, similar items and products will show similar trends. Specifically, the idea is that the curry is made in advance and can be served immediately, but pizza takes time to bake after it is ordered, so it may take longer to serve. We expect the accuracy of the model will be improved by giving the characteristics of the genre of each item. In practice, we use a pre-trained deep learning model to input the number of items and output the embedding. We then took the average of embedding of products in the order to be predicted and fed this to LightGBM. Now, let's talk about the last problem. The last issue is that the time you want to predict strongly depends on the situation of the day. For instance, it depends on the level of congestion in the store or the proficiency of staff in store that day. As you can imagine, such information cannot be obtained directly from the data. Therefore, We are trying to indirectly incorporate such information to the model by aggregating features that are linked to such information in real time and giving them to the model. This time we have created 2 features as real-time features. Let's look at them in order. The first one is a target encoding for the last n minutes, which is average for each store, each area, and the whole. For example, if the last target encoding of that restaurant is larger than all the previous target encoding of that restaurant, we know that the store is more crowded than usual. So we can convey this information to the model. Another feature is that the ratio of numbers of drivers to the number of boarders. Recently, the other feature indicates whether there is a shortage of or the surplus of drivers compared to the number of orders. If there is a shortage of drivers, there may be a long waiting time for the driver to be assigned, or one driver may deliver multiple orders in sequences. In that case, the driver may be late getting to the restaurants. You can tell the model that there will be such a delay. Now, it is possible that the aggregation of features that should be aggregated and passed on in real time will be delayed to some extent before applying to the production environment. We conducted an experiment to see how much of delay is acceptable for features that should normally be in real time. The result is shown in this graph. The horizontal axis represents the delay and vertical axis represents the accuracy. And this is called SNAPE. Feature is a prediction of error message. And if you look at the graph, you can easily tell that the later the aggregated values are passed to the model, that is, the further to the right of the graph, the worse the prediction accuracy becomes. That is, the higher up the graph, the smaller this indicator is, the better it is for us. The accuracy of the model without the real-time aggregated feature was the average of 0.38. So if the aggregated values are passed to the model with a delay of more than 15 minutes, the accuracy of the model will be worse than without the features. On the other hand, if the delay is shorter than 15 minutes, the accuracy of the model can be improved. As for the actual delay, thanks to the efforts of KTSL, the team in charge of streaming processing, we are now be able to aggregate the data in about 30 seconds, which is less than a minute. Therefore, it is expected to contribute to the improvement of the accuracy of the real-time features and models. I talked about the lack of preparation time prediction. We have also looked at these 3 issues. There is no correct data for the ready time. There is a bias in the data depending on restaurants or region, and the time to be predicted strongly depends on the recent situation. Now that I talked about the issue and the actions against it, I'd like to move on to the summary. At Demaecan, the Demaecan is currently undergoing a large-scale system renovation to revamp its service. In the process of renovating the system, they are using machine learning to improve the service experience for all users at the delivery center. In the food delivery business, the orders, merchant, and driver interact in a variety of ways. As a result, there is a wide range of issues to be addressed, and each of them has its own difficulties. But we are trying to deal with them using various technologies such as feature engineering, processing, and multi-objective optimization. In the future, we'd like to continuously improve the accuracy, monitor the accuracy after applying to production, and develop new machine learning components as needed. Thank you very much for your attention.